Right now, SGR 180620 is still spinning, still winding, and the magnetic field coiling around it is building toward a release that NASA has no way to predict or stop. In December 2004, it fired from across the galaxy and burned Earth's sky. And what scientists found inside that pulse is the part they're afraid to say out loud. SGR 180620. Most people have never heard that name. It sits near the center of our galaxy, buried in dense clouds of gas and star-forming dust, invisible without specialized instruments. It is a magnetar, and if you don't know what that means, you need to. A neutron star is what's left when a massive star dies and collapses, 12 miles across, packing more mass than our sun. A magnetar takes that and makes it worse. It is a neutron star with a magnetic field so powerful, so impossibly extreme, that it warps space in its immediate vicinity. If you placed a magnetar at the distance of the moon, it would pull the iron from your blood through the surface of the Earth. That is SGR 180620. That is what was sitting in our galaxy, coiling, loading for years. On December 27, 2004, it fired. In a burst lasting 0.2 seconds, a fraction of a breath, SGR 180620 released more energy than our sun will produce in 250,000 years. All of it, in 1/5 of a second. The pulse crossed 50,000 light years and arrived here with enough force to ionize the upper layers of Earth's atmosphere, Earth's sky, chemically altered by a single object on the other side of the galaxy. Instruments around the planet tripped into saturation and went blind. Satellites tumbled. Radio communications dropped across entire ocean regions. Researchers at facilities from Caltech to the European Southern Observatory scrambled to understand what had just reached them. The signal outshone everything else in the observable sky combined. Gamma-ray detectors built to track the most violent events in the known universe, completely overwhelmed. By one pulse, from one object, that shouldn't have been capable of it. Here's the problem. The energy released didn't match any existing model. Magnetars are known to flare. Scientists had cataloged dozens of smaller outbursts from SGR 180620 over the years. But the physics community had a ceiling, a theoretical maximum for what a magnetar could release in a single event. The December 2004 burst broke that ceiling by a factor of 100. The model said this was not possible. The magnetic field required to produce that output would need to exceed anything known stellar physics allows. But the data was unambiguous. The ionization happened. The instruments failed. Teams at NASA's Marshall Space Flight Center and the Max Planck Institute ran the numbers independently and came back with the same answer. We cannot fully explain this. Not then. Not now. And here is where it gets stranger. Because when researchers studied the shape of the energy curve, the burst signature, they found evidence of something happening inside the magnetar at the moment of release. A starquake. The crust of a magnetar is harder than any material that has ever existed on Earth, but it had been stressed past its limit, and it fractured. Like an earthquake on a neutron star, except the energy released in that single crack dwarfs the largest earthquake ever recorded on this planet by a factor of 10 to the power of 22. That number has no human equivalent. But here's the strange part, it shouldn't be possible at all. Known physics says the crust should bleed magnetic stress gradually, across thousands of smaller events spread over centuries. Instead it held. It compressed. It wound tighter for years, maybe decades, maybe longer, and then in 1/5 of a second it let go entirely. What was winding it that tightly? What was compressing the field past every physical limit we know? The answer physicists keep returning to, reluctantly, is that we may not understand what exists inside a magnetar's core. The innermost kilometer of the densest object in the universe, genuinely unknown. Not poorly understood, unknown. SGR 180620 sits 50,000 light-years away. At that distance, the burst arrived diluted, weakened enough to ionize our upper atmosphere and blind our instruments, but not enough to reach the surface. Diluted enough. Had it fired from 10,000 light-years, the calculation changes entirely. At that range, the energy density on arrival would be sufficient to strip the ozone layer. Not damage it, Strip it, fully, in minutes. There are roughly 24 known magnetars in our galaxy. Most are inactive most of the time. SGR 180620 itself produced additional flares after 2004. Its field is still active. It is still winding. And unlike a tracked asteroid or a near-Earth object we can catalog and watch, a magnetar flare carries no advance warning. The gamma rays travel at the speed of light. Nothing arrives ahead of them. There is no countdown. So the question that doesn't go away, the one with no published answer, is whether that inner core, that unknown kilometer of compressed matter, is building again right now. What happens to Earth's sky if the next release is larger? What happens if it comes from closer? Drop your answer in the comments. Because the scientists who study SGR 180620 professionally don't have one.